Okay, so in our lecture 2, we are going to be talking about shear force and bending moment 1. Our lecture outline is composed of introduction, type of support, type of beam, type of loading on beam, and equivalent concentrated load, and also some work examples as well. In our introduction, we said the design of structures generally involve the planning phase, preliminary structure design, estimation of load, structural analysis, safety and serviceability check, and revised structural design. The design of structures, the design of structures generally involve the planning phase, preliminary structure design, estimating of load, structural analysis, safety and serviceability check, and revised structure design. One of the main tasks of the structural engineer in the design of structure is analysis or structural analysis. The objective of structural analysis is to determine the stresses or stress resultants such as axial forces, shear force, and bending moments, deflection, and support reaction. Recall that in lecture 1, a structure was defined as a system of connected parts designed to carry load and provide adequate rigidity. The concentrated parts, the connected parts are referred to as structural elements. Examples are beams, columns, and slabs, etc. So we are going to be talking about the analysis of beams and also calculation of equivalent concentrated loads as well. So one may ask, what is a beam? A beam may be defined as a structural element which has one dimension considerably larger than the other two dimensions, namely breadth and depth, and is supported at few points. The distance between two adjacent supports is called the span. That is, if you're having a beam like this, okay, and let me say you are having a support such as, let's say, this is a hinge support, and then at the other end you have a roller support. So this can be just known as a simply support beam, okay. At the end of the day, the distance between the hinge support and the roller support is known as the span, okay. That is the distance from here to here, okay. That is what we call the span. So here can be your span. Okay, thank you. So beams are usually loaded normal to their axis. The applied load make every cross section to face bending and shearing. The load finally gets transferred to support. The system of forces consisting of applied load and reaction keep the beam in equilibrium. The reaction depends on the type of support and the type of loading. Thank you. So we are on the type of support for beams. Type of support for beams. Okay. Basic type of support for beams include roller hinge support and fixed support, as we discussed in lecture 1 earlier. For roller support, we said that roller support have one reaction. And also for the hinge support, in lecture 1, I remember we said hinge support have two reaction. And also for the fixed support, it has three reaction. Where I remember we said it has one reaction moving towards the vertical axis, the other reaction moving in the x-axis, also known as the horizontal axis, and then the third reaction is a moment. Okay, and the moment may be what, clockwise or counterclockwise, depending on the position. Okay, okay. So these are the type of beams. Okay, so please let's take note that a roller support can be indicated as this. You can see that this over here looks like a hinge support, but the only difference is that there are two bars there are some balls under the triangle. Okay, so this should tell you that this is a roller support. Don't get confused. Okay, in other words, it could also be drawn like this, indicated with just a round ball, which you may also see it clearly. In other words, it may also be indicated as this. Okay, and you can see it may also be indicated as this. So when you see all of this, please don't get confused. Please don't get confused. Okay, so let's come to the hinge support, which is the B. And you can see that the hinge support, as we discussed in lecture 1 earlier, we said the hinge support has two reactions. Okay, the difference between the roller and the hinge support is that you can see that this hinge support over here does not have any ball under it. Okay, but once you see that the triangle has a ball under it, then it should tell you that it is a roller. But in this case, there is no ball under it. So how can we classify? We can classify it as a hinge support, therefore having what? Two reaction. Okay, so this is a hinge joint. Okay, so this is an example of a fixed support. Okay, it may also be drawn as this or that. Please don't misinterpret them. Okay, or don't get confused whenever you see this. And so please don't get confused whenever you see this and that. Okay, they are all the same thing. They are all the same thing. They are all the same thing. It may be indicated as this or that. Thank you. So let's come to the type of beams we have. Okay, basically, you have a simply support beam, we have a cantilever beam, we have a proof cantilever beam, we have the overhanging beams, we have the continuous beams, and the hot fixed beam. Let's make a little bit emphasis on the simply support beam. When both the support of beams are hinge support, or one support is roller and the other hinge, the beam is known as a simply support beam. Okay, so a simply support beam is basically just a type of beam that is supported at both ends with hinges, or either one hinge and one roller. Okay, so when you see an example of a beam that is having or is being supported by two hinges, or let me say one roller and one hinge, please, you should be able to tell me that it is a simply support beam. Okay, let's come and talk about a cantilever beam. A cantilever beam is a beam with one end fixed and the other end free. Okay, so when you see a beam, okay, a beam, let's say an example of a beam like this. Okay, and let's say maybe here is fixed, here is fixed, then you should know that this is a what? This is a cantilever beam. Okay, you can see that the other one end is fixed and the other end is free. Okay, unlike the simply support we were discussing, the beam could be just indicated like this. Okay, and here may be a hinge. Okay, both ends may be hinges. Okay, both ends may be hinges. Then you see that at the end of the day, one end will be hot roller, roller. Okay, uh-huh. At the end of the day, you see that one end may be roller. So this is an example of a simply support. Okay, a simply support beam. Okay, unlike the cantilevers, this is how they look like. This is how they look like. This is how they look like. Okay, let's talk about the probe cantilever beam. These are beams with one end fixed and the other end simply supported. Okay, uh-huh. So this is just a kind of beam with one end fixed and the other end simply supported. So it could also be just a kind of beam indicated as this. Okay, consider here may be simply supported. This is just a simple support. It's not any too complex thing. Okay, and here is what? A fixed. So you can classify it as a hot probe cantilever hot beam. Thank you. Let's make a little bit emphasis on the overhanging beam. We said that If a beam is projecting beyond the support, it is called an overhanging beam. The overhang may be only on one side or maybe on both sides. Okay, so please let's not confuse these two. Okay, an example of an overhang beam could be this. You can say this is an overhang beam. Okay, and here may be just simply supported as this. You can see that this beam I have just drawn over here, what is happening to it is that the beam is projecting beyond the support. Okay, the beam is projecting beyond the hot support. This part to this part is being projected free. There is nothing supported. So this is why we call an overhang beam. And in the fixed support, in let me say in the fixed beam, a beam whose end are fixed or built in wall is known as fixed beam. A fixed beam is also known as a built-in or encased beam. Okay, so such beams may also be in a form of like this. You can see that both ends are hot, fixed. Okay, so they are going to be classified as this. You see, both ends are fixed. Okay, uh-huh. And this kind of beams do not permit any movement. Thank you. So in a continuous beam, you say a beam supported at more than two sections or points are known as continuous beam. A beam supported, a beam supported at more than two sections or points are known as continuous beam. So a continuous beam could also be uh, in a form of this way. Okay, when you see them in questions, please, I hope you will be able to tell me something. Okay, so this is an example of a continuous beam. It is supported at more than two ends. Okay, it continues like that. So this is an example of a continuous beam. An example of a continuous beam. And let's all remember we said the roller support has one reaction, hinge support has two reaction, and the fixed support has three reaction from lecture one. Thank you. So let's come to the type of beams. Okay. So basically these are the type of beams. You can see the simply support beam. This is the simply support beam we are having over here. Okay. And this is also how to draw the free body diagram. Okay. Or in other words, let me say, uh, at the end of the day, after calculation, you realize that the horizontal force is going to become zero. Okay. That is why at the end of the day, you can see that this horizontal force has not been indicated over here. When we get to lecture 4, I will make a review on this and you get to understand this better. On the cantilever beam, you can see how the cantilever beam has also been uh, displaced over here. We say a cantilever is a beam which has one end fixed and the other end free. Okay. And this is a built, or let me say fixed beam or built-in beam. You can say that both ends are fixed. Both ends are fixed. For the probe cantilever beam, you can also note or spot that this type of beam has one end fixed and the other end being simply supported. The reflection of just one reaction at this angle indicates that it is a roller support that is being used to support it at the free end. And also, the arrow you are seeing on top could be a point load. This is a continuous beam. You can see that this continuous beam has been supported at more than two ends. Okay, so these are the support. All these have been supported with rollers. Okay, in some cases, it may also be a combination of hinges and rollers, but The presence of one reaction would be due to the outcome of a zero horizontal force in the course of calculation. So this is an example of the overhang. Thank you. Okay. So an examples of overhanging beams. Okay. You can see at this part, you can see the overhang protruding. You can see that this part has been hinged and this part has been simply supported. This is also an example of the overhang. Thank you. You can see another overhang at the free end. Okay. This also has another overhang at the free end over here. Very, very beautiful. So in the loadings on beam, we have concentrated loads, or concentrated load can also be known as the point loads. And this is it. We also have the distributed load. The distributed loads are of two forms. That is, we have the uniformly distributed loads, in other words, the UDL, or the uniformly varying load. In other words, the what? The UVL. Okay. Uh-huh. So please let's all get that. And we also have the external moment. In other words, the hot couples. So basically, how many kinds of beams do we have? How many kinds of loadings do we have on beam? Data, we have the concentrated loads, we have the distributed load, and we say the distributed load is composed of the uniformly distributed load and the uniformly varying load. And the last but not the least, which is the hot external moment or hot couples. Typically, loading on beams may be one or combination of one or more of the above loading types. Where distributed loads are involved, these loads are converted into their equivalent concentrated load during analysis. The total load is equivalent to the area of the loaded diagram, and the position where they act is simply based on the centroid of the loaded area. Good. A concentrated, let's talk about concentrated load. We are going to talk about the concentrated load. And we say that a concentrated load or point load is assumed to act at a point, though in practice it may be distributed over a small area. Okay. So in a case whereby a concentrated load is distributed over a small area, you see that the unit is going to be in a form of what? Kilonewton per meter. Okay. Or if they want to make life simple for you, they will just stipulate it as a point load. That is, they will give it to you as a what? They will give it to you as a kilonewton. This is just straightforward. Okay. But if this kilonewton, which is a point load over here, can be distributed. Okay. And when it's being distributed, you realize that what is going to happen is that it's going to become kilonewton per meter. Okay. So you realize that it could be a beam that, and the load will be distributed. Okay. All over the beam. So in other words, before you calculate, you have to calculate for the hot equivalent concentrated load before you could proceed. Okay. You have to calculate for the equivalent concentrated load. So if you see a distributed load, you should know that a distributed load is just a form of a point load. Okay. But in other words, to make life difficult for you, they have converted that point load into a distributed load. So before you can be able to make life easier for yourself, you have to convert this distributed load into a point load. Okay, so that you can be able to make life much more easier for yourself. Thank you. Concentrated load is generally presented as P or W, or in Newton or kilonewton. Okay, so the concentrated load, when you meet them in question, they may be represented as P. If you see P, it is a concentrated load, or even W. It is not a small w. There is a difference between the small w and the capital W. Okay, so this is a capital W, a capital W. Okay, and the capital W we are seeing is equal to the small w times L, and the L is the span. Okay, so the capital W is playing a major role. Okay, or in other words, it could also be in a form of Newton or kilonewton. Concentrated load that do not act normal to the longitudinal axis of the beam but are inclined should be resolved into their equivalent vertical and horizontal components using trigonometry. Okay, so from the basic trigonometry rules, if you have a beam, okay, and the beam, let's say the beam is simply supported, okay, and at the end of the day, the load, or let me say the concentrated load that is being placed on it is inclined at an angle to, let's say, maybe 60 degrees. As a physicist, you have to know that once this is inclined, then it means that this can be considered as the horizontal. Okay, this can be considered as the resultant. This inclined angle of inclination, this can be considered as the resultant. Then if this is a resultant, how do you think this is going to be? This is going to automatically, the other line is going to become the opposite. Okay, let me use a different pen to demarcate that so that we can all uh, have a clear look at that. Okay, so this is going to become the opposite. Then over here, the down part, you consider that to be your hot adjacent. The distance is going to be given. So with that, for that, you don't have to worry. You could always take that distance from this to here and consider that to calculate for your hot equivalent vertical, uh, or to calculate for your uh, concentrated load. Okay, here you are saying concentrated load that do not act normal to the longitudinal axis of the beam but are inclined should be resolved into their equivalent vertical and horizontal components using trigonometry. Okay, so you could just use trigonometry to just derive that. Thank you. Let's talk about the uniformly distributed load. As we have discussed earlier, a distributed load is one which is spread over some length or entire length or of the beam. The rate of loading may be uniform or may vary from point to point. A uniformly distributed load is one which is spread over a beam in such a manner that the rate of loading W is uniform along the length. Each unit length is loaded to the same rate. The rate of loading is expressed as mu per unit length. The rate of loading is expressed as W per unit length. The load intensity may be measured in Newton meter run or kilonewton meter run. Uniformly distributed load is represented by UDL or W. Uniformly distributed load is represented by the the UDL or the W. Okay. Uniformly distributed load is typically considered as a rectangular load, and the load intensity is the same as is the same and uniform across the same loaded length. For the purpose of analysis, uniformly distributed load are converted into equivalent concentrated load and are assumed to act at the center of gravity of the loaded area. So this is an example of a uniformly distributed load. Please, my people, don't get confused. As we have discussed earlier, the uniformly distributed load may be represented as this or this. Okay, you can see that this over here is just looking like something in the form of zigzag. Okay, it's also a uniformly distributed load. So it can be drawn as this or this. Okay, so please don't get confused. So this is an example of a uniformly distributed load. This is an example of a uniformly distributed load. You can see over here is what? A capital W, and over here is what? Small w per meter. Thank you. Uniformly varying load. A uniformly varying load is different from uniformly distributed load, because we said uniformly distributed load looks in the form of rectangle, but the uniformly varying load looks in the form of a triangle. Okay, let's dive and see what we can also discover in there. A uniformly varying load is one which is spread over a beam in such a manner that the rate of loading varies linearly from one point to the other along the beam. Typically, uniformly varying load is a triangular load in which the load intensity is zero at one end and increases uniformly at the other end. Okay, my people, please let's not get confused. A uniformly distributed load could be just, let's say, if this is a beam. Okay, if this is a beam, then it means that our uniformly distributed load, or let me no, our uniformly varying load, okay, can be in the form of a triangle. Okay, so a triangle that is having varying loads. Okay, so that is why we call it uniformly varying load. See, over here, the person standing over here could be a 6 years old boy. Okay, and then the person standing at the end could be, let me say, a fat woman who is 40 years. Okay, so you can see that the 6 years old boy standing over here is going to be less heavier than the 40 years old one standing at the far end. Okay, the middle over here could also be, let's say, a teenager who is 18 years, who is an ectomorph. Okay, so let me say the first person. Let's all say, or let's classify it this way. Let's say the first person is an ectomorph. The first person is an ectomorph, and then the second person is an endomorph, and the third person is a mesomorph. Okay, so you realize that because the ectomorph is not heavy, this part of the beam is going to suffer less. But for the mesomorph is neither heavy nor neither uh, unheavy. So he is just between someone who is heavy and someone who is not heavy. Okay, you can see that the load that is going to be exerted at the second position is just, it's not going to be too much as that of the third position. But the third position is a mesomorph, and you can imagine how the mesomorph is much heavier. So you can see that that part of the beam is going to be suffering more. So you can see that the ectomorph and the the mesomorph and the endomorph at the end of the day, they are all having varying loads. Okay. I said the first person is an ectomorph, the second person is an uh, endomorph, and then the third person is uh, a mesomorph. Thank you. So a uniformly varying load is one which is spread over a beam in such a manner that the rate of loading varies linearly from one point to the other along the beam. Typically, uniformly varying load is a triangular load in which the load intensity is zero at one end and increases uniformly to the other end. For solving numerical problem, the total load is computed for the area of the loaded diagram and assumed to act at the center of gravity of the loaded area. For example, for triangular load, the total load is equal to the area of the triangle, and this total load is assumed to be acting at the center of gravity of the triangle. That is at a distance of one third of the loaded length of triangle from the bigger end and 2/3 from the smaller end of the center of gravity. Okay. Please, my people, don't get confused with this statement. Okay. The meaning of that is that assuming this is the beam, okay, and now this part of the beam is a, a hinge support, and this part is also, let's say, a roller. Okay. So in other words, let's say this is a simply support beam, and now it is carrying a uniformly varying load. Okay. And now it is carrying a uniformly varying load. At the end of the day, you're going to realize that this beam, this part of it, the smaller end, in the calculation, when you are doing the calculation, the smaller end, you are going to use 1/3, okay, to calculate for the position. Then that is from the support. If you are calculating from support A or what, support what, B, it will depend. Okay. Always remember that a position is calculated from a support. Okay. And then this part is rather going to be the 1/3, and then this part is going to be the 2/3. Okay. It's going to be the 2/3. It's going to be the 2/3. So the smaller end is going to be a 2/3. Then the bigger end is going to be the 1/3. Okay, that is if you want to calculate for the position. That is if you want to calculate for the position. If you want to calculate for the position. We shall get there small, small. Always remember that a position is calculated from a support. So if you want to calculate for the position from support A, you are going to use 2/3. So you are going to just multiply 2/3 times the length, okay, which is also known as the span, okay, which is also known as the span. And if you want to calculate for the position from support B, you have to just multiply 1/3 times L, and you get the position. Whether you want to choose support A or support B, at the end of the day, you still uh, get the same answer after drawing the ECL diagram. Without talking much, this is how the uniformly varying load looks like. Okay, this is how the uniformly varying load look like. And I said this smaller end is the 2/3, and the bigger end is the 1/3. As we have discussed over here earlier, they say at a distance of 1/3 of the loaded length of the triangle from the bigger end and 2/3 from the smaller end of the center of gravity. So we are back to external moments. We said basically the type of loadings we have on beams are what? The concentrated load, the distributed load, and the distributed load are composed of two. We have the uniformly varying load and the uniformly distributed load, okay, which we just spoke about. And now we are on the external moments. Good. External moments are generally due to reactions on main beam from secondary beams. Okay. They said external moments are generally reactions from um, main beams to secondary beams. Okay. So you can say that this is a simply support beam. If you want to draw a free body diagram of this, don't get confused. You realize that this is a roller because it has two balls under it. And this is also a hinge support. So this is going to have what two reaction. Okay. So this is going to be your horizontal force at what A, and this is also going to be your vertical force at A. This can also be your vertical force at C. Okay. Then you can indicate your moment. This point is the B. This is the A itself. This is the C. Okay. Then you can now consider your span. Okay. Good. So they say here was what? L over 3, and here is 2 over what? 3. Okay. Just as simple as that. So this is a what? This is a free body diagram. And this could be the original problem. Thank you. So we want to talk about equivalent concentrated load and distributed loads. Okay. Equivalent concentrated load. Equivalent concentrated loads. Where distributed load are given, they must first be converted into equivalent concentrated load. Where distributed loads are given, they must first of all be converted into equivalent concentrated load known as the ECL. Equivalent concentrated load is a conversion of the distributed load into an equivalent concentrated point load. Distributed load may be in the form of uniform loads, that is rectangular load, or triangular load, trapezoidal load, or complex loading. Equivalent concentrated load are generally represented on the beam as point load, but may but with hidden lines and an arrow indicating the direction of loading. Note that for all distributed load are required to be converted to equivalent concentrated load using the given load intensity, ECL and the ECLs are positioned at the central, that is the center of gravity of the loaded area. Please note that if you meet a complex diagram in the question, the only distributed load we spoke about is a rectangular load and a triangular load. Okay, so no matter the figure that is being given to you, assuming you're going to meet a trapezoidal uh, loaded beam, you always have to split it, okay, into sections. Okay, and how many sections have we discussed? We only discussed rectangular and triangular. Okay, so this over here, you realize that we can get how many sections out of it? We can get, let me say, we can get 3 sections. Okay, so here can be what? Section 1. Here can be the section 2. Okay, then you can get, here can be the section 3. Always remember to split the diagram before solving, so you solve them as individual problems. Okay, thank you. Equivalent concentrated load. So we want to make a little bit emphasis on the uniformly distributed load, that is the UDL. Step 1, this is how to calculate it. Determine the distance covered by the UDL. Step 2, multiply the load intensity by the distance covered by the load to obtain the equivalent concentrated load. That is ECL is equal to W times L. Or let me say your load times the distance. Okay. Okay. Note that a uniformly distributed load is a rectangular load. Hence, the ECL is equal to the area of rectangle. Please always note that the distributed load for a uniformly distributed load is always equivalent to the rectangle and hence must be tackled as you are calculating for the area of a rectangle. This is it. Okay. Note that note that a uniformly distributed load is a rectangular load, hence the ECL is equal to the area of rectangle. If the load intensity is given in kilonewton per meter, then the ECL will have a unit of kilonewton. Okay. In the step 3, you then calculate the position of the ECL by dividing loaded length by 2. That is, position of ECL is equal to, the position of your ECL is going to be equal to half times the span, which is the L. Step 4, position the ECL in the middle of the loaded length. It is prefer to relate the position of the nearest support. So if you meet a uniformly distributed load, this is how to go about the calculation. Okay. First of all, you have to determine the distance covered by the UDL. Then secondly, you multiply your W times your span. Okay, you multiply your load times the span. Then later, how do you do? You are going to calculate for the position. Then at the end of the day, you draw the ACL diagram. Thank you. So this is how to calculate for the equivalent concentrated loads a triangular when you meet a triangular load. Okay. So for the triangular load, first of all, you have to determine the distance covered. Then secondly, for how to calculate for the ECL, for triangular loads, the equivalent concentrated load is equal to the area of the triangle. Is equal to the area of the triangle, and the area of a triangle is half base times height. So if you want to relate it to our course, we're going to say that half times W times the span. Okay. If the load intensity is given in kilonewton per meter, then ECL will have a unit of kilonewton. Okay. Yes, the main purpose of our calculation of ECL is to convert the distributed load into the kilonewton, as we discussed earlier. So in the step 3, calculate the position. The step 3 is always composed or entails of the calculation of the position. And the ECL is positioned at the center of gravity for the triangle. The centroid of triangle is calculated. The centroid of triangle is calculated as 1/3 of the loaded length, measured from the bigger end to the centroid, or 2/3 of the loaded length to the smaller end of the triangle. In our step 4, position the ACL at the centroid of the triangle, measuring 1/3 from the bigger end or 2/3 from the smaller end. So that is how you're also going to go about the step 4. Okay. Then at the end of the day, way of how to calculate for the triangular loader, first of all, you have to determine the distance covered. Secondly, what you do is that you have to calculate for your ECL. Okay. ECL, because it's a triangular load, we say that the ECL is equal to the area of a triangle. That is going to be half times W times L. Then in our third step, we have to calculate for the position. I said earlier that a position is always calculated from a support. Okay, so you spot the nearest support. Then what you do is that if it's the smaller end you are considering, you have to multiply 2/3 times the span to get it. But if the nearest support is at the bigger end triangle, that means I have to use 1/3 to multiply the span to get a position. After that, what do? You only come and draw your diagram and indicate your position which you have calculated on it. Thank you. So this is an illustration of how far I have been talking much. Okay, so this is the UDL. Okay, and this is also a triangular load. Okay, so this is how the UDL is being drawn over here. You can see the UDL. Okay, being supported at the three ends, being supported at both ends, which is A and B, being supported at both ends, known as the A and then the B. Good. From there, we also realize that uh, the equivalent concentrated load for the UDL is equal to this. Okay, so to calculate for the equivalent concentrated load, we will just multiply the W times the L for the UDL. Okay, and also to calculate for the position, To calculate for the position, you just have to multiply half times L. The position is equal to just half 1 over 2 times L. Okay, that's how you can see that they are writing L over 2. Okay, so this is how you calculate for the position for UDL2. That's how you calculate for the position of a UDL. Then from there, make a little bit emphasis on the let's make a little bit emphasis on the triangular load. Okay, you can see that this triangular load is having varying loads. Okay, it's having varying loads, and because of that, to calculate for the EC, ECL, which is also known as the equivalent concentrated load, we have to multiply half times WL. So the ECL for the uh, equivalent concentrated load for a triangular load, this is how you calculate for it. Your ECL is going to be equal to half times base times height. Okay, and the position for the smaller end, you have to use 2 over 3 to multiply L. Okay, that is it that they've done over here. 2 over 3, okay, times L. Okay, but at the bigger end too, you have to use the, let me say, 1 over 3. Okay, 1 over 3 to multiply the L. So basically, that is the main aim of lecture 2. Okay, how do you do? First of all, you have to calculate for your ECL. Secondly, first of all, you have to know your loaded length. Okay, you calculate for your ECL, you calculate for your position, and what do you do? You come and draw your ECL diagram, then you are good to go. So this uh, a description of the equivalent concentrated load. Okay, so for other type of distributed load, first of all, you can see that this is a complex structure, as I just told you earlier in the previous slides. This is a complex structure, hence you have to divide this into two sections. Okay, this could be section 1, and this could be what, section 2. Okay, so you take them part by part and solve for it. Okay, other than that, you are going to face challenges. You can't calculate all this together like that. So in your step 1, you have to study the loaded and subdivide the loaded area into sub areas, that is rectangular and triangular load. Step 2, use the given step for the rectangular load and triangular load to convert the various segments into their equivalent concentrated load and determine their appropriate position. Step, that's all. Note, for complex loading, a triangle may have to be used to determine the load intensity at desired point from the given figure. So we can now start with some work examples. We can now start with some work examples. Okay. So first of all, this is a work example. They say determine the equivalent concentrated load of the beam shown below. Okay. And they say we should take uniformly distributed load W to be 10 kilonewton per meter. And then they say we should take the span to also be 6 meters. Okay. This over here is a simply support because it is supported by a hinge and a roller. I told you initially that hinge support has 2 reaction and the roller has 1 reaction. Okay. So first of all, let's say if you're in the examination hall and this is your answer booklet and you're given, the first thing you are supposed to do is you are supposed to redraw the original problem. You are supposed to redraw the original problem. Okay. So we say this is our original problem. And right over here, original problem. Original problem. Good. Okay. Then from there, where do you come to? You come to your solution. In your solution, first of all, you have to study the problem, the original problem very well. And you should be able to tell the examiner the kind of loaded beam it is. So over here, you can see that this is a uniformly distributed load. Okay. And then the loaded length in the step one is what? 6 meters. Okay. The loaded intensity is what? 10 kilonewton per meter. You write it over there. Okay. You write it over there. So let's say this is one. Let's say this is two. Let's say this is our step three. Okay. So in our step four, what are we going to do? We're going to calculate for our ECL. And we said that because it's uniformly distributed load, our ECL is just equal to the area of a rectangle, and the area of a rectangle is length times breadth. In this case, our ECL is going to be equal to W times L, okay, which is equal to just 10 times 6. So how do you get your span? How do you get your ECL? You just multiply this 10 over here times the 6, okay? And at the end of the day, you are going to get your answer in kilonewton. Who is going to be what? 60 kilonewton. Thank you. So over here, you can see that that's why they are getting 60 kilonewton. Then the position, we said that the position, to calculate for your position, you always multiply half times L. Okay, and our L over here is our span, which is the 6 meters. So half times 6 is giving us 3. So it's telling us that our load is going to be concentrated at a midspan. Okay, so after your fourth step, what do you do? In your step five, you come and withdraw your problem again. Okay, come and withdraw original problem for another mark. Okay, then in your step six, finally, what you are going to do is that you are going to draw the ECL diagram. Okay, and then the ECL diagram, you can see that initially this was a point load, but to give you problem, it has been converted into a distributed load to test your understanding. So you will have to convert the distributed load into a point load to tell us that you understand the subject or the course content of the semester. Thank you very much. So this is just an example of how the ECL diagram is going to look like after the calculations we did. Okay, so you can see that they said that it is at midspan from support hot. It is at midspan. Okay, so whether you're calculating it from support A or support B, you are still going to get what? 3 meters because it's a simply support. Okay, okay. So that's why you are saying that the 60 kilonewton that we had for our ECL, this is the answer we had for the ECL. ECL. Okay, it is acting at a position of what? 3 meters. It's acting at a position of what? 3 meters. That is why they just measured 3 meters from the a support. Okay, then they had it at a midspan. Okay, good. So let's come to the work example two. In the work example two, you can see that this is a triangular load. And they say we should determine the equivalent concentrated load of the beam shown below. In the given, they say we should take uniformly varying load to be 10 kilonewton per meter, and then the span to be what? 6 meters. They say we should take our span to be 6 meters and our uniformly varying load to be 10 kilonewton per meter. Okay, good. So this is also a simply support beam which is carrying a uniformly varying load. So first of all, what do we have to do to be able to calculate for such a problem? First of all, you have to be able to know the kind of distributed load is it, and it is a uniformly varying load. Then secondly, you have to know the loaded length. Okay. After knowing the loaded length, you calculate for your ECL, your position, then you just come and draw your ECL diagram. Okay. So this is how we are going to go about it. So in your given, you put down whatever they gave you. They say we should take our uniformly varying load to be 10 kilonewton per meters and our span to also be 6 meters. So this is what happened. You draw the problem again and right over here, original problem. Okay, write it attached to it. For a mark, you have to redraw the problem. You have to redraw. You have to redraw the problem. Thank you. So this is our original problem. This is our original problem. Then when you come over here, this is the solution. Okay, this is our solution. So in our solution, how do we go about it? First of all, we can all see in our step one, we have you have to be able to tell the examiner the kind of loaded uh, diagram it is. Okay, and you can see that this is a uniformly varying load as we discussed earlier. Okay, good. From there, what do we do next? You have to know the loaded length, and the loaded length over here is the loaded length over here is 6 meters. Okay, then in our step three, what do we do? Load intensity. The load intensity is 10 kilonewton per meters. Then in our step four, we're going to calculate for our ECL. Because this is a rectangle, we say we calculate for it as we are calculating for the area of a triangle. And it's just equal to half times W times the span. Okay, so you can see that over here, you're multiplying half times 10 times 6, giving us 30 kilonewton. Okay, giving us 30 kilonewton. Then from there, we calculate for the position. You can either choose to calculate from the position from support A or support B, but just always remember or write somewhere that the position is always calculated from a support. Okay, so over here, Mr. Gude decided to calculate for the position from support A. Okay, so that is why you can see that he multiplied 2 over 3. That is, he's calculating from the smaller end, this smaller end over here. Okay, because we said the smaller end is 2 over what? 3, and then the bigger end is 1 over 3 in terms of calculating for the position. Okay, so he is calculating from the smaller end. That is why he's using 2 over 3 to multiply the 6. Okay, and 2 over 3 times 6 is what? 4. So from there you come to your 6 point, and your 6 point, what do you do? In your 6 point, what do you do? You realize that you are going to just redraw the original problem again. Then you have to redraw it. Then from there you come and draw your ECL diagram. The ECL diagram, because we are calculating from support A for the position, we just measured 4 meters from support A. Then we had what? We had uh we measured 4 meters from the support A, okay, and placed the ECL over here. So over here you can see this is the ECL. The ECL. So the main purpose of calculating for the position is to just know the position of the ECL, where it is concentrated most. Okay. If you had chose to use, let me say, calculate from the bigger end, it's just going to be what? 1 over 3 times the 6. And you realize that 1 over 3 times 6, 1 over 3, okay, times 6. Okay. Please let's all punch 1 over 3 times 6 on our calculators. And what are we going to get? We're going to get 2. Okay, so you realize that even at the end of the day you are still going to get the same answer. Okay, so you are still, that is, in this way, you are going to measure from support B 2 meters. Okay, so whatever approach you choose to use, you are still going to be getting the same parameters in the same what range. So this is the ECL diagram. The ECL diagram is a must and you should be able to draw it. Okay, that is what is going to tell the examiner that you really understand what you are doing. Let's take a look at the problem 3. Okay, you can see that problem 3 is problem 3, on the other hand, is more or less like a complex uh, loaded beam. Okay, Please don't get confused. This over here can be divided into two sections. Okay, that is, let's say you are going to have what, two right angle triangles. So this can be tackled as what, first right angle triangle, and this can be tackled as second right angle triangle. So you have to solve them as what, separate parts. Then at the end of the day, you draw the ACL diagram as one part and represent their position. So at the end of the day, you're going to have two positions in this kind of what, uh, problem, because the problem has two sections in it. Thank you. So they say we should determine the equivalent concentrated load of we should determine the equivalent concentrated loads on the beam shown below. Okay. So first of all, what do you do? First of all, you have to come to your given, then you withdraw the problem. And we say the problem is what? This is the original problem. Original problem. Original problem. Then what do you do next? This is a hint on how to solve the question. Okay, they say first of all, what do we do? Divide the loadings into two parts. Thank you. Part AB, a triangular load, and part BC is also a triangular load. Use the step given in previous slide to solve the problem. Finally, illustrate the solution using a free body diagram. Use hidden line with arrows to represent the equivalent concentrated load, and the direction must be the same as the original problem. Okay, so this our part. Let me say this problem over here. You can see it has been split into two parts. Okay, that is, our first part can be in a form of this. Okay, it has been split into two parts and solved. Okay, so this is, let me say this is the A part. This is A part where the support is. Okay, good. And on the other hand, this is the B part. Okay, the problem has been split into this other hand. So let's say here is B. Okay, so here is also what, B, and here is also what, C. But I realize that here is a what, a roller. Okay, here is a roller. So here is C. Okay, so the problem has been split into two. Then you can tackle AB first, and later come and tackle what, BC. So let's this is our first section we are going to solve first. Then this is also our what, section 2. Okay, let me reclaim this and write it well. So this is the section 1. Okay, so in taking the part AB, how did we go about it? Then you write solution before you start with that. So the part AB, okay, the part AB is a triangular load. Thank you. And the loaded length is 5 meters. The loaded length is 5 meters. The loaded intensity was 20 kilonewton. 20 kilonewton per meter. Okay. Then the ACL. To calculate for the ACL, as we discussed earlier, it's just a triangle. So it's just going to be half base times height. So we're just going to multiply half times 20 times the span, which is 5 meters. We are getting 50 kilonewton. To get the position, over here, the position can only be calculated from support A, because I told you earlier that we calculate for the position from a support. Okay, if you take the section 1, you realize that it only has a support at A. Okay, so you only calculate for this position from support A. So that is a smaller end. So it's going to be what? 2 over 3 times the length. So that's why you're multiplying the 2 over 3 times length. Okay, so over you can see that 2 over 3 times 5, giving us what? 33, giving us 3.33 meters. Okay, then if you also consider the support B, if you also consider the second section, which is the part BC, the part BC is also a triangular load, and the loaded length is 10 meters. The loaded length is 10 meters. Okay. And the loaded intensity, as usual, is 20 kilonewton per meters. 20 kilonewton per meters. Then from there, uh, what else do we do? The ECL, we calculate for the ECL because it's a triangle, half base times height, so half times 20 times the 10. We are getting what? 100 kilonewton. And the position over here, you realize that the support is at C. And I told you that we only calculate for a position from a support. So in this case, we are going to multiply, it's also from a smaller end, okay? So we are just going to multiply 2 over 3. 2 over 3 times 10. So that's why you're seeing 2 over 3 times 10, giving us 6.67 meters. Okay. From support C, you have to tell the examiner the support you are calculating is from, to tell him how competent you are about the work you are doing. Okay. To tell him that you understand what you are doing. Okay. So after calculating from, so you realize at the end of the day, we calculated for 2 positions. Okay. So if you realize there are 3 sections, we are going to be calculating for what? 3 positions. Okay. So it continues like that. So this is the position 1. Let me say this is the position 1 and this position 2. Okay. This is position 1 and this is what? Position 2. Okay. So from there you come and draw the original problem again. This is the original problem. Then you draw the ECL diagram. In the ECL diagram, you realize that it's only one line that was being drawn, one long line being drawn like this. Then just as usual, then you just represent, you draw, you represent your reactions. Okay, because we have a hinge support over here, you can see that there is only one there are 2 reactions. Okay, and this reaction is known as what? It's known as HA, horizontal force at A. This over here is known as the VA, which is the vertical force at A. Okay, this is also a vertical force at C because it's a roller having just one reaction. Okay, so the first one in our section 1, we calculated for the position from support A. That is why you can see S measuring the what? That's why you can see S measuring the 3.33 meters. Okay, from the support A. That's why you can see us measuring the 3.33 meters from the subpoint A. When you measure that with the ruler, then you can put your 50 kilonewton, which you had for the ECL in the section 1, on it. Okay. That is that 50 kilonewton is going to be more concentrated at what? 3.33 meters in the 5 meters, which is the span for the section 1. Also for the section 2, you realize that your 6.67 meters that we had for the position was calculated from the support C. So you are going to measure 6.67 meters with a ruler, okay, from support what? C up to this part. Then you are going to position your what? ECL you had in the section 2, which was the 100 kilonewton, okay, ECL, okay, for 5 marks free, okay. Thank you very much. So I'll be meeting you guys face to face. Then I'm sure we can be able to solve some of the trial questions and also uh, resolve uh, some of the areas you find challenges. Please do well to through the rest of the examples on your own. When we meet in person, bring out your challenges and then we see how to figure that out. Please, and a very big please, I have given you guidelines on how to go about the solving of the problems. I'm hoping you'll be able to solve the trial questions and give me a feedback, okay, so that you can be able to test your creativity or know, test your understanding on the course, okay. You realize that your understanding of lecture 2 is based on lecture 1, and your understanding of lecture 3 is based on lecture 2. Your understanding of lecture 4 is based on lecture 3, Okay, so please don't stay behind. Okay, make sure that even if we will be meeting uh, on top of the roof, you join us. Even if we'll be meeting at the seaside, you join us. Everywhere there is going to be tuition this semester, please, in a very big place, try and be part. Okay, because the semester is quite scary, and because of the workload, you have to manage things. Someone will say tackle, tackle. Okay, other than that, you are going to face challenges. Okay, don't hesitate to see me in groups, one on one, in person, in case you find challenges with any of the courses, and I'll be available to assist you. Thank you very much.